All right, let's talk about the screen you're staring at right now. Its history is, well, it's probably not what you think. This isn't a story that starts with silicon and software. Nope. We're starting with spinning metal discs and flickering lights.
So, how did we get here? How did we go from these, flickering mechanical ghosts on a machine to screens that can literally just disappear? That's the journey we're going to take. From the earliest, craziest contraptions all the way to tech that honestly feels like it's straight out of science fiction.
Our story kicks off not with an electronic problem, but a mechanical one. The first challenge for those television pioneers wasn't about pixels or anything like that. It was, how do we use gears and motors to turn what we're seeing into an electrical signal?
And the first real solution came way back in 1884 from a German student named Paul Nipkow. He patented this amazing device, the Nipkow disc. Just try to picture this. It's a spinning metal disc, right? But it's got holes punched in it, in a spiral. As it spun, each little hole would scan one single line of an image, turning light into a fluctuating electrical current. It's genius, really.
And for this brief, buzzing, whirring moment in the 1920s, inventors like John Logie Baird actually brought these things to life. He got the first grayscale image transmitted in 1925 and even did a public demo a year later. But these systems, with their fuzzy 30-line images, they were hitting a wall. You just can't spin a metal disc fast enough without it flying apart. And the difference between the old way and the new way was, well, it was night and day. Just look at that jump in resolution. From, 240 lines max with a spinning disc to over 400 with electronics. The mechanical way was noisy, it was bulky, and the image flickered like crazy. It was an incredible proof of concept for sure. But it made it crystal clear that a totally new approach was needed.
So, the answer to all those mechanical problems was the electron beam, something they called inertialess because, it has basically no weight. This new tech had 0 moving parts, and it would go on to be the undisputed king of displays for more than 50 years.
And that's when the cathode ray tube, the CRT, steps onto the scene. Instead of spinning discs, a CRT fires a beam of electrons through a total vacuum. Magnets steer this beam to draw an image, line by line, on a screen that's coated with stuff that glows, phosphors. With no physical parts to wear down or make a racket, it could draw pictures way faster and with much better detail. So what was the next big jump? Color, of course. But here's the problem. How do you introduce color without making the millions of black and white TVs people already owned totally obsolete overnight? The answer was this brilliant little thing called the shadow mask. It's a thin sheet of metal inside the tube that makes sure 3 separate electron guns, one for red, one for green, one for blue, only hit their own colored dots on the screen. It was such an elegant solution, and it's what kicked off the whole color TV era. But the CRT had its own big problem, and I mean big. It was massive, and it was heavy. See, the bigger you wanted to screen, the deeper and heavier that glass tube had to be. And that big limitation, it sparked a huge battle for who would own the living room. So in one corner you had plasma. Every single pixel was a tiny little cell of gas that lit itself up, which meant you got these incredible deep black levels. In the other corner you had LCD. It used these tiny liquid crystals like little shutters that would either block or pass light from a big light source behind the panel. Now for a while, plasma was the king of picture quality, no question. But LCDs, they were just way more power efficient, you could make them super thin, and they were cheaper to produce. And in the end, that's what mattered. LCD won the war.
Okay, so LCDs won the war, but they had this one major flaw. They always needed that backlight to be on, which made getting truly deep dark blacks almost impossible. So this quest for perfect black became the new obsession in screen technology.
The first step was to ditch the old clunky fluorescent tube backlights and switch to smaller, way more efficient LEDs. You could either stick them along the edges of the screen, which gave us those super thin TVs, or you could place a whole grid of them directly behind the panel. That gave you a much more even brightness, and it opened the door for the next big thing.
And that big thing was full array local dimming, or FALD. This was the real breakthrough. Instead of the whole backlight being either on or off, FALD divides that grid of LEDs into hundreds, sometimes thousands of individual zones. This lets the screen intelligently dim the parts of the picture that are supposed to be dark, while keeping the bright parts, well, brilliant.
And what's so cool about this is seeing how a company like LTS just kept solving one real-world problem after another. It wasn't just, hey, let's make it better. It was, okay, broadcasters need HDR monitors they can actually carry around. Boom, Gen 1. All right, now retailers need super efficient screens for their shelves. Bam, Gen 2. From handhelds to hyper-precise medical displays, every single leap forward was because somebody had a real problem that needed a solution. That's innovation.
So, the bottom line here is that all of this tweaking and refining led to displays that are brighter than ever, incredibly efficient, and have contrast that can finally start to compete with other technologies. We're talking deep, dark blacks right next to bright spots that can hit over 3,000 nits. That's seriously bright.
This whole relentless search for perfect black, it eventually led everyone to the ultimate question. What if a screen didn't need a backlight at all? What if every single tiny pixel could just light itself up?
And that, my friends, brings us to OLED. OLEDs use these thin films of organic stuff that glow when you run electricity through them, so each individual pixel becomes its own tiny light bulb. And this is a total game changer, because if a pixel needs to be black, it doesn't just block light, it just turns completely off.
So this really sets up the big choice for anyone buying a high-end TV today. On one side, you have Mini LED, which is basically the peak of LCD technology. It gives you incredible brightness. On the other side, you've got OLED, with its infinite contrast and those perfect inky blacks. They both have their pros and cons, and they really define the cutting edge of what's possible right now. Now, once you get rid of that entire backlight assembly, something really amazing happens. You're not stuck with a thick, rectangular box anymore. With the backlight gone, the very shape of the television is starting to change.
And the next great frontier? It's probably micro LED. This stuff promises the best of all worlds. You get the per-pixel control of OLED, but with the insane brightness and long life of traditional LEDs. The only thing holding it back is manufacturing. I mean, the challenge of placing millions of microscopic LEDs onto a screen without a single one being out of place, it's just incredibly hard and expensive to do at scale. For now. But hey, while we're all waiting for micro LED to get affordable, the future is already here in other ways. In 2024, LG released this thing. It's a wireless, transparent 4K OLED TV. It's a screen that, when you're not using it, can become as clear as a pane of glass.
And just like this quote from LG says, the goal isn't just to show you a picture anymore. It's about blending the digital world into our physical spaces, making the tech just disappear until the moment you actually need it.
And that leaves us with one final thought. From a clunky, spinning disk in a lab to a transparent window to the internet, the screen has come an impossibly long way. It really makes you wonder, when the frame around our content finally and completely disappears, what in the world are we going to see next?